Welcome back. In this video, we will see in detail a problem as well as the theories for the equivalent static force analysis. So, the clear introduction for this method and the design philosophies for the earthquake resistant construction is discussed in the previous video. You can watch that video before watching this video. So, the concept of dynamic analysis into partly dynamic and partly static analysis for finding the maximum displacement. So we already mentioned that there are two methods for finding the earthquake forces. One is a dynamic analysis, which is the accurate one, but time taking and difficult process to perform the analysis. The equivalent static method is basically converting the dynamic forces to an very equivalent static forces. And the limitation of this is it is restricted only to single mode of vibration. We have seen the different assumptions for equivalent static force method in the last video, which I'm not discussing in this video. Just a quick recap, the step-by-step procedure for equivalent static force analysis. Depending on the location of the building site, identify the seismic zone and seismic zone factor Z, and we can find the zone factors for different zones, compute the seismic weight of the building as per the IS 1893 2002 as old code. We have 2016 now, and then we have to find the then we have to find the natural period of the building. We have seen the equations for finding the natural period for different type of material and for different stories, and then obtaining the data pertaining to the type of soil conditions for finding the SA by G value from the graph or chart. So you can find the time period, you can identify the soil type to find the SA by G value, then importance factors and the response reduction factors to find the AH, which is Z by 2, this is a zone factor, SD, SA by G from the chart, I importance factor, and R is the response spectrum value. After obtaining the H and W, we can find the design base shear, and then we discuss the QI value for finding different story shears and story forces based on this equation. So the limitations of equivalent static lateral force analysis is the empirical relationships are used to specify dynamic inertial forces as static forces. So this conversion is there to dynamic to equivalent static forces, and these empirical formulas do not explicitly account for the dynamic characteristics of the particular structure. That means that mode shapes and the building frequencies are not directly taken for the equivalent static lateral force method, which will definitely induce some errors. These formulas were developed to approximately represent the dynamic behavior of what are called regular structures and structures which have a reasonably uniform distribution of mass and stiffness. So if it is very irregular in geometry, then the equivalent static method won't be a right choice. The structures that are classified as irregular violate the assumptions on which the empirical formulas used in the static forces. So these equivalent static forces are more or less good only for very regular buildings. So the example, the plan and elevation of a 4-storied reinforced concrete office building is shown in figure 1.1. The building is shown below. Number of stories is 4, zone is 3, live load is 3 kN per meter square. Please note that the zone, the Kerala belongs to zone 3. That you can find in the IS 1893 2016 code. The column dimensions 450 by 450, beam 250 by 400, thickness of slab 150, thickness of wall 120, importance factor is 1, and the structure type is OMR of building. Determine the seismic lateral load and story shear force distribution. This is the plan of the building, and this is the elevation. So analyzing, considering the stiffness of the infill masonry, you can compute the seismic weight. So it's like the calculation of the different dead load and live load of different components as well as the acting forces. We can find the slab dead load due to the by finding volume into density. The beam also total length of beam into the section area will give you the volume into density will give you the dead load of beam. Similarly, the columns also we can find total length of column into cross section will give you the volume into density of concrete will give you the column weight, and the walls based on the volume of wall into brick masonry 18 kN per meter cube will get the wall weight, live load. So you can compute the total load of all floors by all the accounting all the beams, all the columns, all the walls, all the slabs. For this particular problem, we're getting 3619 kilonewton, and the load on roof slab. This is the live load calculation. So we got 3619. Sorry, 3619 is the dead load, and the load on roof slab is getting as this value. This is 2793.5. You may note that in previous video we have discussed how to calculate the live load for different conditions. So if it is more than 3 kN per meter square, it should be accounted in a different value, and for less than 2 it should be only half. So the total seismic weight is getting as by adding the, we have 3 floors, so 3619 into 3 plus 2793.5 will get into 13650 kilonewton, and you can find the fundamental period as a moment resisting frame. It's in the third equation which we discussed in the previous video. 0.09 into h square root d will get 0.2277, and the spectral acceleration SA by G from the graph or chart is based on the medium soil which is given here. Sorry, the medium soil type is not given in the question. In that case, you can assume the soil type and you can mention in the answer paper. And from the time period and from the type of soil, you can find the SA by G value. The sound factor is getting as 0.16 from the table of IS 1893. Importance factor is 1. The response reduction factor is 3 for OMRF, which is given in the question. So we can find the AH value as 0.0667, and the base shear is given by AH in W. AH we got from here, and total weight will come to 910 kilonewton. Then we have distribute the total base shear to all the floors. You have first floor, second floor, third floor, fourth floor, and the WI is the individual like the loads, where you can see here a lesser value due to the top floor, and height 3 meter, 6 meter, 9 and 12 from the floor. WI in the HI square will give you these values, and W in the HI square divided by sigma of all these values will give the distribution of the force 910.033 under these values, and once you add all these values you will get again this 910.033. Yeah, these are the cumulative shears. So the first load, the top story values taken as shear there, then the bottom story will be this value plus this value will give you the combined shear, then this 3 value will give you the combined shear. Once you add all the values, that will be the base shear. So it's the replicate or the diagrammatic explanation for the shear forces. You know these values, and these are the pictorial representation of the lateral forces. 426, 737 are the story shear, and this is the forces, which is 426, 310, 138, which is as represented here. Yeah. So this is like analysis without considering the stiffness of infill masonry. So the only change will happen in the natural time period. When you are accounting infill masonry, the equation will change, and so this is having a new equation, and the value will change. Then this value and also the type of soil is taken for finding the SA by G value. This value will change, and then so the nearly the other values will change accordingly. That's about the problem on equivalent static load method. Thank you.